Good afternoon, guys. So we're looking at the last two lessons of circular motion and gravitation today. We're going to start by finishing off gravity, and then we're going to look at just general circular motion questions and kind of apply everything that we've looked at up till now to this. So here we go, lesson 7. Let's just get straight into it. It's a carryover from what we were looking at in the last lesson. Looking at what we've got for a rocket leaving a planet, some distance r from the center. It starts the radius of the Earth and moves out to some distance big R. And we wanted the work given. If we remember from last week, I'm not even going to necessarily ask it, but if we remember how it looked, we had an energy initial plus work equals energy final, and now we've got this new expression for a gravitational potential energy. We're going to assume that this guy is not moving. Somehow it moved, and now it has been placed here and it's stationary again. So we don't care about the motion in between. It was stationary, it is stationary. So we've got potential energy initial plus work equals potential energy final. So we've got negative GMM over R plus work, that's R initial, plus negative GMM, or equals rather negative GMM over R final. We're going to add this to the other side because it's negative. So we're going to get negative GMM over big R plus GMM over little r. So that's this expression right there. What we want to look at now is what it means to escape planet's velocity. Now, practically speaking, there's going to be a difference between practically leaving its gravity or actually leaving its gravity. So to escape from a planet's gravity means in theory to travel an infinite distance from that planet. In order for this term here, the potential energy due to gravity at the end to be zero, this big R needs to be infinite. Practically speaking, mathematically infinite. But that's not possible or even strictly speaking realistic. We know we've sent things from Earth way out there and they're not infinitely far away. They're very far away, but they're not infinitely far away. But the effect of Earth's gravity is practically meaningless. So what we're looking at is, or the idea here is that practically we're going to travel far enough away from the pull of gravity, or so that the pull of gravity has become very small. So but effectively what we're doing is it's going to be negligible. Some of the other language here, so escape, let's go back here. Escape means to travel an infinite distance from a planet. To barely escape is some new language here. Means to escape from a planet with no kinetic energy left at the end. So effectively what you're ending up with is at rest an infinite distance away, is what we're looking at here. So escape, this language of escape implies that your potential energy equals zero, but you could theoretically still be moving, like so many probes that are really far away from our planet. Or there's this idea of barely escaping. The implication here being that the potential energy equals zero and your kinetic energy equals zero. You're infinitely far away and now not moving. So we've got a 12,500 kilogram rocket blasting off from Earth and barely escaping the Earth's gravity with no additional engine use. So one large explosion, boom, it starts moving and then barely escapes. So the hardest part with a lot of these questions is identifying where different energies, like where they are, or what they are rather, based on the language in the problem. So let's look at the problem we've got. We've got the mass here of our rocket. That's going to be useful. We've got this idea of barely escaping, which means that PE final and KE final are going to equal zero. And we've got this language here of no additional engine use. What that means here in the way that wording is interpreted is there's no work being done here. We've got one massive explosion that gives us all the kinetic energy we need, and then this thing just goes. We want to know how fast rather the rocket has to be moving at launch for this to be true. So this implication here is that work equals 0. There's no work done. So this is all just energy like we've looked at before. Energy initial plus work equals energy final. So we know we've got potential energy initial plus kinetic energy initial. We know that work is equal to 0. And we know that there's no energy at the end because PE final and KE final are both equal to 0. So let's plug in what we've got here, the potential energy. We were leaving a planet, now we're going sufficiently far away, we're going to have to take into account gravity. Or our new equation for gravity, rather. Negative GMM over R initial plus, well, kinetic energy is always just 1/2 mv initial squared, and that's equal to 0. So we want to know what that initial velocity has to be. So we're going to add this over to the other side. We're going to get 1/2 mv initial squared is equal to negative gmm over r initial, and that shouldn't be negative because we added it over. That's positive. My apologies. And if we look at here, what happens is the little m's are going to cancel. The little m is the mass of the rocket. And so they're cancel. And I can multiply the 2 over, and then I'm going to square root. So my initial velocity here required to effectively escape gravity, assuming no additional work is being done, is the square root of 2g big M over the radius of our planet. So if we plug in some values here, we're going to get the square root of 2 times 6.67 times 10 to the negative 11. We're told we're on Earth, so that's 5.98 times 10 to the 24 divided by our radius, which is 6,380,000 meters. If you run that, you're going to see that the velocity required to do this with no additional work being done is 11,182 meters per second, which is rather quick. I want to double check that number. 6.67 negative 11, 5.98 times 10 to the 24 divided by 638,000. Yeah, there we go. Divided by so this thing's moving relatively quickly. To put that in other terms, if we looked at this in kilometers per hour, we multiply by 11,000. We multiply 11,182 by 3.6, and we're going to see that this is 39,000. One sec. 182 times 3.6. Sorry. This is 40,255.2 kilometers per hour. This thing is moving incredibly quickly, assuming there's no work being done. So effectively what you've got here is a cannon. This is how fast that the object would have to leave the cannon, the rocket would have to leave the cannon in order for all of these statements here to be true. We know this isn't practical. We launch things from Earth all the time, but this constant engine use is generally what we have. If we wanted to do it without, this is how fast an object would have to be moving at the start. So let's take a look at another type of example here. We want to take that same rocket, that 12,500 kilogram rocket, we want to send it from Earth and we want to put it into a stable circular orbit 25,500 kilometers from the center of the planet. So there's a whole bunch of things that we're told here. We want to write out the work energy equations. We want to find the orbital speed, the KE in orbit, the PE in orbit, the total energy in orbit, the PE at launch, and the work required to put this thing into orbit. So, and there's a reason why it's broken up this way. Generally speaking, the questions won't be, but the reason this question is to kind of show you the whole process. So here we go. We've got energy initial plus work equals energy final. And now we want to take a look at what's actually going on here. This thing starts stationary, a stationary rocket. So the energy initial here is only potential energy. It's only got some potential energy because it is some distance from the center of the planet. So there's some initial potential energy here. In this particular question, we're not taking into account the explosive nature of the launch, because the last part of this question is to find the work required to put it in orbit. So work is just a type of energy. To look at that energy, we can put it in a couple different spots. Today we're just putting it into, or we're considering it as to be part of this work term, and we're going to figure out what that value is. And then at the end of this thing, for it to be in orbit, it has to be some additional distance from the center of the planet. We've got our initial and we've got our final. And orbit implies that this thing's moving. It has some velocity here. So this thing's going to have some kinetic energy at the end, and it's going to have some potential energy at the end here. So this is where the work energy equation is going to start. I'm just going to move some stuff around here. We're going to get work. I'm going to subtract the potential energy initial from both sides, and we're going to get that the work is equal to the kinetic energy at the end plus the potential energy at the end minus the potential energy at the beginning. So let's go through and take a look at the rest of this. So we've got kinetic energy final, potential energy final, and subtracting the initial potential energy. So kinetic energy final is given to us by half mv squared. We're going to add to it PE final. If remember what the gravitational potential energy is, I'm just going to go over here and collect some equations for us. Potential energy is equal to negative gmm over r. So if we're adding the potential energy at the end, well, ultimately what we're doing is we're adding negative gmm over r final. So we're going to have half mv squared minus gmm over r final. And now we're subtracting negative gmm over our initial. So that's ultimately going to be plus gmm over our initial. And now these minus signs often screw people up. Be careful to take those into account. If we look at what we've got here, the kinetic energy in orbit is given to us by this term here. The potential energy in orbit is given to us by this term here. The total energy in orbit is the sum of these two, which we already took into account by putting it here. The potential energy at launch is this term here. And so what we've got is, instead of having to break it up piece by piece, we can deal with it as one kind of big gigantic equation here. The only thing we need to consider is, what is this term right there? That v is actually going to be the orbital speed. We have to figure out what that is, because we've got values for all of the rest of this. We know that the radius at the end is 25,500,000 meters. We know the radius initially is 6,380,000 meters. We've got the mass of the Earth, the mass of the rocket, and g. The only thing we're looking for yet is that v right there. Well, it's important to remember, though, this thing is orbiting, so that's moving in a circle. So we've got some uniform circular motion going on here. Here we go. We want to find v. So now there's, when you're dealing with this kind of thing, there's two ways to consider this. We could either use this equation here. V equals 2 pi r over the period. If we have sufficient information, we can use this. Well, we know what the radius is, but we don't know what the period is, so we can't use this here. What that means is we're going to have to use orbital dynamics, or the dynamics of circular motion. So we're going to have to use this. F net C equals MAC, and we're going to have to use the fact that AC equals V squared over R. Now the force that's actually causing the motion here is gravitational. So I'm going to put this up here as well. We're going to have FG equals GMM over R squared, just so we don't forget that. So we're going to have GMM over R squared equals MV squared over R. Now my M's are going to cancel. That R is going to cancel with that squared term there. And we're going to get V equals the square root of GMM over R. So if we run the values through here, we're going to get the square root of 6.67 times 10 to the negative 11. 5, actually, I already said that this is gone, so it shouldn't be here. 5.98 times 10 to the 24 divided by the radius. Well, we're at 25,500,000 meters. And that is going to give us an orbital velocity, or should give us an orbital velocity of 3,955 meters per second. So now we're going to take this value for V, and we're going to insert it back up there, and then we've got everything that we need to figure out the work done. You got to be careful here. This is going to give us a rather large equation, and punching that thing into your calculator is where lots of students make a mistake. I'll show you what this whole equation is going to look like here. So we've got the work equals 1/2. Little m is the mass of the rocket. So we've got 1/2 times 12,500 times 3,955 squared. So that's the half mv squared. Minus 6.67 times 10 to the negative 11. And we've got the mass of the planet and the mass of the rocket. So we're going to have 5.98 times 10 to the 24 times 12,500 divided by our final, which is 25,500,000 meters. Again, this term is not squared because it's potential energy, not force of gravity. So then we're going to add to that the 6.67 times 10 to the negative 11, 5.98 times 10 to the 24, the 12,500 multiplied there, divided by the 6,380,000 meters that the rocket was initially from the center of the Earth. So that is the rather monstrous equation that you're going to plug into your calculator, or you can do it piece by piece and then get values for each one of these things, which is how the question was set up originally. We wanted the KE in orbit, the PE in orbit, then the PE at launch. So we would have had values for this, this, and this. But we could, there's no reason why we can't do it all at once. And when you'll do it, or if you do it, I would like you to punch this through your calculator just to make sure that you can. You should get work equals 6.84 times 10 to the 11 joules. A lot of energy is required to set this rocket up into this position. We're going to skip the next example and go to page 323, and we're going to look at just what it means to write some of these work energy equations out. So what I would encourage you to do is actually to pause this video here and see if you can do these on your own. Write out the work energy equations for each one of these situations based on the wording here. So please do pause now, and I will, when you come back, I'll just finish this off here. So I'm hoping you've paused. We'll continue it. So for each one of these things, if we have a rocket at rest, all of these things are starting with, I should put this up here, energy initial plus work equals energy final. We're starting with this as our premise, and so for each one of these, we're going to put together the work energy equations. I'm just going to give them to you because I'm hoping that you've done them on your own. If you have questions, comments, concerns about any of them, I'll happily go through them in more detail. So this first one here, the rocket at rest, means there's no kinetic energy, so we've got potential energy initial. It's blasting off and rising. So because it's at rest, we have to take into account the energy required to raise it. So that's where that work term is going to come from. If we don't have kinetic energy, we definitely need work. And it rises to some maximum height, and so we're going to get PE final here. Maximum height implies it's not moving at some point. Well, at the end. The next one is a rocket moving at speed v at liftoff near the Earth's surface. It rises to the height with no engine use. So no engine use implies that work is equal to 0. These things always start with some sort of potential energy, but we've got the initial V. So that's going to give us kinetic energy to start with. If we've got the kinetic energy, well, if we've got no additional engine use, we've got no work done here. Work equals 0. So we're going to get PE final at the end because there's some maximum height. We've got a rocket at rest on the Earth, blasts off and barely escapes to infinity. We've got, because it's at rest, blasting off, that implies that we have no kinetic energy to start with, and it's work done that's actually causing this thing to rise. So we've got our potential energy initial plus work, and if it's out at infinity at rest, that's just equal to 0. This guy here. We've got moving with speed v at liftoff, so we're going to have potential energy to start. We're going to have kinetic energy to start. We've got no additional engine use, and we've got barely escaping, so it's out at rest at infinity, so that's equal to 0. We've got a rocket at rest, blasts off, and enters a circular orbit. So that's going to be potential energy initial. It's blasting off. So there's some work done there. It's going to enter a circular orbit of radius r. Should be of, not or. So that's going to give us kinetic energy at the end and potential energy at the end. We've got a rocket moving at speed v at liftoff, rising with no further engine use. So we've got potential energy to start. We're going to have kinetic energy to start, and it's entering an orbit. So we're going to have potential energy to end and kinetic energy to end. And then we've got a satellite moving at speed v at a distance r, and it's falling back to the Earth's surface. So for this one, we've got potential energy to start, we've got kinetic energy to start, and we've got, it's falling, so there's no work being done here. It doesn't talk about air resistance or anything. So we've just got potential energy final and kinetic energy final, because it's definitely hitting the Earth with some velocity. And it does, even though it's hitting the Earth's surface, it still has some potential energy final, because you remember when we're dealing with gravity here, it's all about the distance to the center of the Earth. So unless that satellite plows all the way to the middle of the Earth, it's still going to have that potential energy term there. So I want you to take a look at some of these questions. Try them on your own. You're looking at questions 1 to 4. I want you to do number 6. I want you to do number 6, and I want you to do number 7. One of the things that you'll notice is that there's actually 2 number 6s, because there's a typo in the book, and I want you to look at both of them. As always, comments, questions, concerns, feel free to fire me an email or come to my office hours.